Hi everyone, welcome to Leetcode Weekly 393. Maximum sum of values by very small. That seems hard. Okay, we want the minimum possible. Okay, I could do a binary search. This seems just annoying, to be honest. Yeah, this seems freaking annoying. Hmm, 10 is really small. I know you can do order n by m, but do I have order n by m? I know, okay, for a given start value, there's like a fixed range of AND values that work. Yeah, then I think I need to do like do I need another sparse table? Maybe. Maybe I do actually. I think I do need. Okay, I'm going to just duplicate this. We're gonna have one min and one vector inst. Yes, dp and some you. I guess st dot query. Okay. Min DP, I guess. Int db2. I might need to do +1. Not sure yet. se.query I low not equal to can't, then I guess here. And continue. Okay. Okay, so now I need to do Oh, I need this to have a better constructor. Okay. That was, I don't know, this problem seems quite hard. It's not judging. I have an infinite loop. Oh, yeah, low 2. That's really annoying. Okay. So I need the first one to have a bitwise XOR. I need the last one to have a bitwise XOR of 2. Okay. This one is not correct already. I can see that the 5 shouldn't be correct. Oh, I see. Okay. Okay, this one is intriguing me because I don't think it. Like already this line is wrong, but I don't know why. Zero, 1, 2. Mine is 0 next, so why is it tying? Oh, I guess I should be using positive infinity for impossible, not negative infinity. Oh, 17, -1. Okay, I think this is correct now. Jesus, that was hard. I bet people have already finished. No, I think you can do some sort of inclusion exclusion thing. How do I do it? What's the expected return type? Long. I mean, that isn't correct anyway. Okay, why do I have negative answers? This should be LCM, maybe, I guess. Oh, okay. Mm. It seems just annoying. I guess if A is a question mark and B is a question mark, or like this digit is less than 2. I guess I want it less than 1. I don't know if this is a good way of doing it. If A is 0, then we set B to 9. I'll reset E to 1. And this one doesn't matter too much. If C is equal to question mark, then we set C to 5. If E is question mark, then we set D to 9. Okay, we're just gonna submit. Okay, at least I solved all problems. Not super fast, but I did it. 5th place. Yeah, so this would beat me by 3 seconds, but that's fine. Okay, I guess I'll just discuss my answers. These questions, I just did a case bash, but you can also just brute force through all times and check if they match. I just do stuff like, if the first digit's missing and I can replace it to a 1 without violating anything, then I do so, otherwise I have to set it to a 0. For B, like, if the first digit was a 0, it can be at most a 9, otherwise it can be at most a 1. And then I set C and D to be 5 and 9 if possible. This problem is very straightforward. You just loop through the elements, check if they're prime. And if so, then you take the last index and the first index, which was prime, and just take their difference. This problem is an inclusion-exclusion problem. Basically, the idea is, for a given set of coins, if you want to, you want to answer the question, how many denominations less than or equal to x? Like, how many less than or equal to x can be made? And if you can answer this question, you can just binary search on the answer to find that, to solve. And yeah, the way we can do this is with the inclusion-exclusion principle. Basically, the answer is like, if you loop through all subsets S of coins, if you like count how many less than or equal to x can be made using any of the coins, i.e. any of the coins in S could be using all of the coins. What I mean is how many numbers less than or equal to x could be made, like could be made using the first coin in the subset, could be made with the second coin in the subset, made with all possible different coins in that subset. Sorry, that's not very clear, but for example, if the set S was 2, 3, I'm asking how many numbers could be made both using only multiples of 2 and both only multiples of 3. And that's equivalent to being a multiple of the lowest common multiple of all of these numbers. And basically, if you add this if the length of the subset is odd, and you subtract it otherwise. This is the inclusion-exclusion principle. You can search it on. So that's how I've implemented it here, and then I just binary search. Finally, this problem, like, my code is very messy. Okay, I think I got rank 5. Just like, okay, it's not the best. Basically, you notice that, let's say you're considering some suffix, and you want to choose so the first prefix is equal to some value, say there's 7. Essentially, there's like some, if we fix this left because we're only considering the suffix, we want to choose like some prefix of this suffix that has an and equal to 7. It turns out that this range of prefixes that are possible forms some contiguous subarray for the right index. There's some contiguous range of right indices that work. This makes sense because and is like, if you fix L and you increase and you consider the bitwise ands of these subarrays, like that will be non-increasing because and always decreases. So somewhere there's a sweet spot where its and is equal to what you're looking for, and then once it gets below that, then it'll never hit that again. Now, for a given L, we can find this range by binary searching over the smallest r, such that this subarray has a bitwise and equal to whatever you're looking for, and also do like another binary search to find the maximum index. And in order to find the and of a subarray, I just use a sparse table. And from there, it's pretty straightforward. I have a bottom-up DP, and in fact, I have another sparse table, but basically, it's a bottom-up DP, but I only store like it's a 2-dimensional DP, but I only store it in a 1-dimensional table, and instead just keep updating that table multiple times. So for a given value of z, I guess the post condition is here dpz, like dpi stores the answer for, I guess, the subarray from I onwards, and we only consider AND values from index Z onwards. So here I already store the answer for Z equals M take 1 as a base case. If that suffix has the correct AND value, then the answer is just the last element, because that would be the value of the subarray. It has to end at the end. And otherwise, I'll say it's infinity, representing impossible. Now, if we want to, okay, low and low 2 are essentially the, like, if I loop, I is like the leftmost endpoint here. I'm trying to find this DPI. And low 2 is the range of possible endpoints of this first subarray with an AND equal to what I'm looking for. And essentially, I want to turn this into a range min query because I want to find the min. So here, I actually store a DP. This is a min sparse table over the DP of the DP row for the previous row. So first, I for example, like currently here, DPI stores the answer for nums I onwards and AND values from Z plus 1 onwards. If I add on for each DP value, I add on the value of its previous element. That's basically accounting for, I guess, it's accounting for stopping the subarray there, because then the value of that first subarray will be equal to nums I take 1. And then if I just throw a min sparse table over that, then this condition is just a range query. I don't know if that made sense, but it makes sense to me. And yeah, the time complexity is like n times m times log n, so it's fine. Anyway, yeah, that's all I have for you this week. Thanks so much for watching, and I'll see you guys next time. Bye.